right? Although this filter will not be assessed in test 2 in the following test, but anyway, I'm going to demo to you how to design the filters and then use it in the daily usage in the most of the experimentations. Okay. So before we start, I've already attached the attendance link at the chat. So make sure you slide in for the attendance. Okay. All right. So are you all ready? Could we start with the lecture this morning?
Yes, doctor.
All right. So basically, filter is a very important signal conditional circuit. Although we most of the time we are just talking. Usually, this is more related to the electrical engineers, but because recently our system is involving more and more electronic components, right? Even though in the car or in the lab equipment, all of them are basically involved a little bit of the electronics, right? Especially when we are dealing with the sensors for the measurements. So these sensors requires you to have some basic knowledge about this signal conditioning. All right. So for these filters, the main use of it is to filter out the noise. All right. As you can see that in this graph, the green color is the noisy signal. Okay, a signal produced by the sensors, and usually these sensors will the signals will be very noisy, and this signal contains a lot of spikes, as you can see that the green color, and therefore we need to before you present these results to your panel or you use this result for the analysis, it is better for you to filter out these spikes. All right, and we can see that this spikes is actually a repetitive. So when it is repetitive, then we can use the filter to filter it out. Unless the noise you have a look on that and then you found that it is quite random, then there will be some difficulties in order to filter out those kind of random noise. Okay, so that is the main use of these filters in order to get to filter out that spikes and give us the clean signal. And clean signal is represented by this black color graph. All right, so that is the main functions for these filters. Okay, so filters, they are basically in your what you are going to learn about these filters. There will be two types. One is the passive and another is the active. So passive filters, it doesn't require any external power supply. All right, so we don't really need to have a batteries in order to power up such signal conditioners. So this type of passive filters usually use passive electronic components, for example, inductors, resistors, or capacitors. Active filters, on the other hand, it requires external power supplies, for example, batteries, in order to power it out. So, for example, this type of active filters is just like the use of op amps and the transistors. Okay, so we are going to also learn how to design an active filters using the op amps. Okay, so passive filters. The advantage of using active passive filters is that we don't need external power supply, right? Active filters, on the other hand, it requires power supply. Okay, but when it comes to the disadvantages of these passive filters, we can see that the output filter signal is always having a gain less than 1. So it means that the signals we filter after we filter that signal, the signal will experience energy loss. So initially, maybe the sound is very loud, the signal is very strong, okay, which is somewhere around a sine wave with a voltage could be somewhere around 1 volt. But after you use a passive filter and then you filter it, this amplitude will be will become smaller. So maybe somewhere around just 0.5, and therefore the signals become very weak. And we usually need to amplify the signal again. Okay, so there is a disadvantages of using these passive filters. And then secondly, steep stop band is not possible. There is a cutoff frequency. So this cutoff frequency, if we want to achieve a very steep cutoff, then we cannot do that. And secondly, cascading is also very difficult because of the impedance interactions. So we know that in the op-amp, inverting or non-inverting inputs to the op-amp actually has a infinite impedance. So that means it actually cut out the impedance that is coming from the previous workload. So in that case, passive filter, because it doesn't have this kind of features, and therefore cascading different filters together could cause interaction between the workload. Okay, so it causes your design becoming very inaccurate. Okay, so advantages of active filter, definitely it can be actually active filters not just filters, but it also amplifies the signal. Okay, for the passive filter, it cannot amplify. You need to have another amplifier. And then a stop band, very steep is possible. And lastly, it can be cascaded because there is high input impedance at the op-amp. Okay, so there is a difference between the passive and active filters. So put it simply, passive filters just use passive components like the resistors, capacitance, and also the inductance. All right, this doesn't require any external power supply. Whereas for the active filters, mainly we are using op-amp. Okay. There is a difference between passive and active filters. So before I move on, do you have any questions about these passive and low pass, passive and active filters, which you are still not clear? Could you all see my slide? Okay. All right. So do you all okay? Clear about what I've explained so far? All right. Okay. So for the filters, passive filters usually that we are using it in your syllabus, there is a low pass and high pass filters. Okay, low pass and high pass filters. So for a low pass and high pass filters, so for example, like let's say we have a graph, and this is the signal, and then there is the amplitude, and we have a signal that is looking something as this. Okay, the red color is the clean signals, and most probably after we do the measurements, this clean signal could be corrupted by the noise, and in that case we will get something like this. Okay, so you can see that if we do the spectral plot, or we perform Fourier transformations, okay, fast Fourier transformations, and then try to get the spectral plot of this graph, most probably we are going to get two plots. So after we perform the Fourier transformations, instead of representing it in the time domain, right now we are representing it in the frequency domain. Okay, so this is a frequency domain, and then the y-axis will be the magnitude. Okay, so in this case, we are going to get two spikes. Okay, so you can see that in the time domain, the clean signal, which is the red line. So this red line is a sine wave, right? Let's say this sine wave is carrying a frequency of 1 kilohertz. Okay, so 1 kilohertz means that one complete cycle, this is equivalent to 1 millisecond. Okay, so this is 1 kilohertz signal, and therefore we can see that because this red line is a low frequency, at the lower frequency, so we are going to have a and then it has a frequency at the it is indeed a 1 kilohertz sine wave, and therefore at 1 kilohertz, all right, at 1 kilohertz we can see a spike, and we know that this is the clean signal. And for the green signal, the green color, you can see it forms a small ripples. And this small ripples basically is a combination of two sine waves. One low frequency sine wave at the 1 kilohertz, and then another high frequency signals in the is at the higher frequency. So let's say this green color graph is essentially a combination of both 1 kilohertz and the 10 kilohertz noise. Okay, so that's why we have this 1 kilohertz. It is exactly the clean signal that we want to extract, and this 10 kilohertz is the noise that we want to get rid. Okay, so if we perform the FFT, for the green light, we are going to get a graph which is looking something as this. All right, exactly, there will be one spike at the 1 kilohertz, indicating that there is a spectral plot in the 1 kilohertz. And then yeah, I think for the red color, because it's a clean signal, and therefore usually it doesn't have any high frequency. Okay, so it will only have this. Whereas for the green color, the spectral plot will be looking something as this, and then there will be another spikes over here. And because this noise signal is having a frequency of 10 kilohertz, and therefore by the FFT, there will be two spikes for this noise. Okay, and in this case, we know that 1 kilohertz is the signal that we want to preserve, and then we want to get rid of the noise which is at the 10 kilohertz, and therefore we can actually multiply this FFT, okay, with windows, and this windows it is when it is low frequency, which is extending this up to 1 kilohertz. We multiply by a magnitude of 1. Whereas for the regions more than 1 kilohertz towards the 10 kilohertz, this is the noise that we want to get rid, then therefore we multiply with a 0. So in that case, after multiplying this, we are going to get a new graph. Okay, magnitude and then the frequency. So now we are going to get a new spectral plot, which is something as this. Okay, so the green spectral plots, we multiply with the windows, the blue windows 1 and 0. And therefore, you are seeing that we preserve the 1 kilohertz. But at the same time, we get rid of the 10 kilohertz. Okay. So that is in the frequency. And now once we have already done converting this, then we can perform the inverse Fourier transformations and to transform from the frequency domain back into the time domain. Okay, so because we have already get rid of this noise, and therefore if you plot the graph, we are going to get back this sine wave. Okay, clear? Are you clear about these filter processes? Okay, I try to explain to you the very basic principles about this, how filters can be used to filter out the noise. All right, are you all right? Clear so far? Okay, so if you don't have any questions, then I'll just proceed. All right, that is how we can use a filter, how a filter could eliminate the noise. Okay, because it is operating in the another dimensions of a frequency. All right, anyway, these windows, when we have this kind of a windows where at the low frequency, we are multiplied by a magnitude of 1, and then high frequency is multiplied by a magnitude of 0. This is what we so-called as a low-pass filters. All right, so that is what we are going to learn over here, the low-pass filters. All right, that is low-pass filters. If let's say we have another windows where initially at the low frequency it is a 0, and then at high frequency it has a magnitude of 1. So if we are multiplying to this type of windows, this is what we so-called as a high-pass filters. The main use of this low-pass filter, you can see that low-pass filter, it preserves the low-frequency components and remove all the high-frequency components. So if let's say your noise is in the high-frequency regions, and therefore we need to use a low-pass filter in order to remove the high-frequency noise. But if let's say your signal, instead of you are actually, the clean signal is in the high frequency, and then you want to remove low frequency noise. In that case, we are going to use a high pass filter. All right, so that is the main difference between the low pass filter and the high pass filters. Using the low pass filters, we get rid high frequency noise, and using high pass filters, we get rid low frequency noise. Okay, and therefore the regions where the filter starts to cut, this is what we name it as a cut-off frequency. Okay, so this is a cut-off frequency. So when this cut-off frequency is very important, because whenever we want to design the filters, we need to know where exactly is this cut-off frequency for either the low-pass filter or the high-pass filter. Okay, any questions? All right, so if you don't have any questions, and now we will just go towards more towards the applications of this low pass filter. How can we use this low pass filter? All right, for the low pass filter, what you need to memorize, okay, I don't mention about understand, is that simply because most probably if you don't know how to derive this equation, it's fine. But if let's say we just want to use it, what is most important is you need to memorize this circuit. Okay, first you need to memorize this circuit, and then secondly you need to memorize this cut-off frequency. Okay, cut-off frequency FC is equal to 1 over 2 pi RC, and you can see that the cut-off frequency for this RC, which is a resistors and capacitors, right? And because you're using a resistor and capacitor only, and it doesn't require any external power supply, so that's why it is a passive. So these are passive resistors, capacitor, low pass filters, right? If you are using this type of a low pass filter, low pass filters, then what you need to memorize the circuit. Okay, there is the circuit diagram, and then secondly, the cut-off frequency functions. All right, and lastly, the gain or the transfer function of this low pass filters. Okay, where V out over to V in is essentially equivalent to 1 over square root 1 plus F over Fc squared. So these are the three equations, the three things that you need to memorize in order to know how to design this RC low pass filter. Okay, so how exactly we can use this, I will show you later in the examples. All right, for the RC high pass filter, the same things, right? It is also using resistors and capacitor components. The only difference is that now in here is swapped with the low pass filters. Low pass filters, we have a resistors connected to the input, and then the capacitors is parallel to the ground. Whereas in the high pass filter, the circuit is swapped. So capacitor is now connected to the input voltage, and then resistors is swapped, is parallel, and then connected to the ground. Okay. So similarly, you need to memorize this circuit for the high pass filters first. Secondly, you need to memorize these cutoff frequency functions, and you can see that cutoff frequency functions is exactly the same like the cutoff frequency functions in the low pass filters. And finally, the transfer functions of these high pass filters. So that is the three things that you need to memorize in order you can design for this RC high pass filter. Okay. As for the active low pass filter and high pass filter, I think I'm not going to show it to you, but I'll just go through it very quickly also. First, you need to memorize this circuit. Okay. Secondly, the cutoff frequency functions. You can see that it is also the same like the cutoff frequency above here. The only different thing is that the cutoff frequency, the resistors and the capacitor, it refers to these resistors and these capacitors. Okay, so don't use R1 in your calculations. And then for the transfer functions, is exactly the same like previously in the low pass filter, which is 1 over square root 1 plus F over Fc squared. All right. You can see that if we compare with the RC low pass filter, it is exactly the same. The only different thing is that passive, it is not going to amplify the signal. So that's why it has a gain equals to 1 over here. Whereas for the active low pass filters, all right, the gain, yeah, is 1. But before this, it has another gain, which is the ratio between the feedback resistors and the input resistors, RF over R1. So in that case, we can actually amplify the signal as well. So to use these active low pass filters, you need to also memorize these three things. Okay. And for the high pass filters, similarly, you need to memorize this circuit first of all. All right. So the main difference between active low pass and the high pass filter is that instead of having the capacitors in the feedback, okay, in the low pass filter, the capacitor is in the feedback. Now the capacitor, it is swapped to the front. Okay, it is directly connected to the input voltage. Okay, so for the cutoff frequency, the equation is also similar, but the only different thing is that the resistors and the capacitor right now, it is referring to the resistor R1 and C rather than the resistors in the feedback loop. Okay, so make sure you also memorize these formulas. And lastly, the transfer functions for these high pass filters also needs to memorize. And you can see that this terms is actually exactly the same like the high pass filter for the passive high pass filters. So for the passive high pass filter, we have F over Fc and then divide square root 1 plus F over Fc squared. Right, it is exactly the same over here. The only different thing is that because it is active, and therefore for the active, we actually also multiplied by a amplification gain of RF over R1. All right, so the output actually is a minus sign, but because it is absolute and therefore we can ignore this minus sign. So same thing goes to here. All right. So far, any questions about these formulas and also the circuit for the high pass and low pass filter? Everyone? Is that okay? Any questions? Clear, everyone? Okay, so that is the equations and circuits that you need to memorize in order to answer. To use it in the design. So now let's move on. All right. So here it lists out all the summaries for all passive and active low pass, high pass filters, the circuits, the cutoff frequency, functions, and also the transfer functions. All right, so you can see that they are all exactly the same. The only difference is that in the active, use RF, and for the active high pass, use R1C. And then the passive, it is multiplied by a gain of 1, whereas for the active, it has a gain of RF over R1. Okay, so these are all the, this summary is most important measure when you want to design the filters, and then you know, you save this, all right, and you memorize it, and then it will be very handy. Okay, so when we try to design the filters, make sure you use a standard capacitors. So this standard capacitor is usually in the range from 1 microfarad to picofarad. Okay, so for example, such kind of a standard capacitor is just like 0.1 microfarad, 0.22 microfarad, 0.47, 0.01, and 1 nanofarad, 2.2 nanofarad, and so on. Okay, up to 1 picofarad. The main reasons why we focus in this range simply because when your capacitors is actually having a capacitance value greater than the 1 microfarad, this essentially already turns into supercapacitors, right? So the behavior of the supercapacitors is quite like a battery. It's just like a battery. It's just that the behavior is like the battery, but it doesn't mean that it is exactly a battery. Okay, so there is a supercapacitors. It usually has a capacitance greater than 1 microfarad, and then when for the capacitance value smaller than the 1 picofarad, this capacitor is too small and almost can be neglected. So that's why it's good we select a capacitance value within this range. All right, and most of the time the capacitance value commonly found in the market is 0.1, 0.22. There is another 0.33. All right, and then 0.47. And for the rest, I think it's already very difficult to get it from the market. Okay, unless you it is custom made, right? But most of the time is 0.1, 0.22, 0.33, and 0.47. Okay, and for the standard resistance, on the other hand, make sure that you use a resistors with the resistance from the 1 kilo ohm to 1 mega ohm. Okay, the main reason why it is 1 kilo ohm to 1 mega ohm is that any resistors below 1 kilo ohm, it is the resistance too low. It's almost like the there is no resistance. Okay, I cannot say that there is no resistance. I can only say that the resistance is actually too low. Right, when it is too low, then the behavior will be a little bit weird for this kind of a filter purpose. Okay, or even in the design of the signal conditioner. All right, and then If let's say your resistance is greater than 1 mega ohm, it means that there is almost hardly a current will be able to flow through this high resistance. All right. So there is a reason why it is good to have your resistors value within this range, 1 kilo ohm to 1 mega ohm. Okay, so for example, like the standard resistors is just like a 1 kilo ohm and then 1.2 kilo ohm, 1.4, 100 kilo ohm, and so on. All right, so that is about the filter design criteria. Usually the range of capacitors and the resistors that you usually use. So now let's have a look on these first examples. How can we design a RC low pass filter? Right, so in this example, we are asked to design these low pass filters to reduce the noise to 96% at frequency of 100 kilohertz. And therefore, we are asked to determine what is the cutoff frequency and then what is the attenuation of input signal by this filter at frequency of 1 kilohertz. So what is this question? This example is all about is that this is a spectral plot of the noisy signal that we want to filter, right? So for the spectral plot, we are having two spikes, okay? And because all pass filter, so that means the signal that we want to preserve, we want to keep it is the low frequency signal. This is what we want, okay? So this is the desired, this signal we want to keep it. And we want to get rid of this noise. The noise is at high frequency. Okay. And then what it means over here is that the frequency, the noise at the 100 kilohertz, it needs to be suppressed to 96%. Right. So this is 100%. This magnitude maybe is a 100%. And therefore, after we apply these low pass filters, we want to suppress this spike down to only 4%. So that means 96% of the noise has been suppressed or reduced. Okay, so only 4% of this noise is allowed to go through the filters. Whereas the others 96% has to be removed. So that means after it goes through this, then we are most probably getting the new spectral plot, something as this, and then a spike, okay, which is only 4%. Okay, clear? You understand these questions? Is that okay? Everyone?
Yes, doctor.
Okay. So now let's move on. How can we do the design? So because the questions actually wants us to first of all, we need to determine the informations that we have obtained is that we want the output over input at 100 kilohertz is only having a magnitude of 0.04. Okay. So that is only 4%. For 4% is 0.04. So that's why output over input, there is a suppression. Eventually, if let's say input is 100%, so output will become 4%. Okay, so V out over Vi will be 4% at 100 kilohertz. And then we just need to substitute the formulas for the transfer function of these low pass filters. As you can see that this is the formula. So we just substitute it in. Okay, put it over here. And now we can, for the frequency F, this is exactly equivalent to 100 kilohertz. So we just substitute it in and we can solve for the cutoff frequency. And once we solve these equations, we found that cutoff frequency has to be equals to 4,000 hertz, 4,003 hertz. Okay, and therefore, in order to achieve this cutoff frequency of 4,003, so we just use this cutoff frequency functions. right? So which is from the second equations over here. All right, we just substitute in, and then we can now determine what is the resistors and the capacitance. So by try and error, we try the capacitance equals to 1 nanofarad. Let's say we select a capacitance equals to 1 nanofarad, and then we substitute into here. And therefore, we are going to get, we try to solve for the R, right? And therefore, we are getting R is equals to 39.76 kilo ohm. Okay, so 39.76 kilo ohm. And that means, so now it means that because this one is in the range of 1 kilo ohm to 1 mega ohm, and also this capacitance is from the 1 microfarad to 1 picofarad. So that means this selection is actually valid. It actually falls within the range. It's just that 39.76 kilo ohm is not a standard resistance. And therefore, let's say we choose a resistance, a standard, which is 40 kilo ohm, and then the capacitance is 1 nanofarad. And therefore, we recalculate back after using this standard resistors and the capacitance, what will be the effect to the cutoff frequency. So we substitute back into the cutoff frequency functions and found that actually now the cutoff frequency is 3,978. This is quite, also quite close to the desired 4,003 hertz. So let's say we just select this and then we plug it into the transfer functions. And the question asks us what is the effect of these filters on the signal that we want, which is 1 kilohertz. Okay, so we substitute it back 1 kilohertz. Now we consider for the output over the input functions for the 1 kilohertz. And therefore, the frequency is 1 kilohertz, and then divide by the cutoff frequency square. And now we found that actually this is equivalent to 0.97, which is 97%. So it means that when we are applying this is a spectral plot, frequency, and then the magnitude. Okay, so originally we have a signal. Okay, this is the original signal. We have two spikes. Okay, one spike is at the 1 kilohertz. This is what we want, desired. And then we have another noise at the 100 kilohertz, which this is the noise that we want to get rid. Okay, so applying the low pass filters. Okay, and low pass filter meaning that we are applying a window, something like this. Okay, and this low pass filters is having a cutoff frequency somewhere around 4 kilohertz. According to the calculation over here, cutoff frequency is 4 kilohertz. So eventually we are using 3,978. Okay, so 3.978 kilohertz. So after this is having a windows of 1, and then the rest will be up to here becomes a 0. So eventually, when we apply this low pass filters into here, and we try to calculate for the output over input ratio, the transfer functions at 1 kilohertz, we found that it is 0.97. So it means that these filters actually suppress this input signal, the desired signal, 1 kilohertz. This one initially is 100%. It becomes 97% after we filter it. So most of the amplitude is actually still quite close to 100%. So that means it is acceptable. Whereas over here, if let's say right now you try to calculate back for the VR over VI for the 100 kilohertz, and then we so 100 kilohertz we substitute into here, and then the cutoff frequency is the same thing with supplies over here. And if you press the calculator, you are going to get a value which is close to 4% or 0.04. Okay, so it means that Right now, it will be suppressed and only 4% is allowed to go through. All right, so far so good. This is how we design for this low pass filter. How can we determine the resistors and the capacitance? So everyone clear? Are you clear about these calculations? Yeah. Any questions so far? Any questions? Why so quiet? Give me some response. Do you understand or you want me to repeat again?
Sir, can you repeat again?
Okay. So, right. I think I'll just repeat from the beginning. Is that okay?
Yes, Doctor.
All right. Okay. I know that this filters is actually a kind of topics that we mechanical engineers never study before. So that's why yeah, a lot of the entry level is quite high for us to understand this. So that's I want you all to really grasp the concept for these filters. All right. So according to the questions, we have two signals. No, okay. We have one noisy signals, okay, or corrupted signals, and these corrupted signals contains two sine wave, okay, or two spectral components. The first, which is 1 kilohertz, this is what we want to preserve. This is the desired signal. Okay, 1 kilohertz is what we want. And then 100 kilohertz is what we want to filter out. So that is the noise, right? The noise is at 100 kilohertz. And we want to eliminate this noise. Okay, so that eventually we only have a clean desired signal at 1 kilohertz. And it is telling us we want to design a low pass filters so that we can cut this magnitude. Okay, so 96% of this magnitude has to be removed, and only 4% of it is allowed to go through it. Okay, only 4% of it is allowed to go through. So that means after we so we need to design a low pass filters, and low pass filters is actually something looking like this. Okay, low pass filter is usually have a it's actually have this kind of response. I mean the windows. Okay, it may not be initially. Okay, so it will be flat, and then at the cutoff frequency, it will start to going down quickly and eventually goes to 0. So this is the windows. Initially is 1 or 100%, and then afterwards, it is desired that in the questions, when it is filters at 100 kilohertz, the magnitude here supposedly should be only 4%. Okay, only 4% is allowed to go through, and when it is below the cutoff frequency, this is the cutoff frequency. Okay, so when it is lower than the cutoff frequency, it is desired that 100% to be going through it. But the problem is that these RC low pass filters, actually it is not flat. All right, it will be a little bit of slanting. There will be a little bit slope. The slope is not significant, but it will still affect the desired signal at 1 kilohertz. Okay, so the question asks us, what will be the effects of the low pass filter that you have designed on the 1 kilohertz and also on the 100 kilohertz, although the question didn't ask us to calculate, but you may calculate it also. Okay, so knowing these design criteria, we want to suppress the high frequency noise from 96% to 4%. So that means the transfer functions. Okay, I think I'll just use a blue color. Okay, so the transfer functions VR over VI, it means that only 4% is allowed to pass through. Okay, and then this is at the noise frequency, which is 100 kilohertz. At 100 kilohertz, only 4% is allowed to go through. Okay, because it's VR divided by VI, right? So when VI is 1 volt, so VR has to be 4%. That is the meaning. All right, so once we know that there is the information, and now we just substitute these informations into the formulas for the low pass filters. So we know that VR over VI 100 kilohertz is desired to be 4%. And then this frequency, this is the frequency where we want to filter, which is 100 kilohertz. Okay, so 100 kilohertz we substitute into here, and then we can from here we have only one variable left, that is the cutoff frequency, and we can determine from here the cutoff frequency is desired to be at 4003 hertz. Okay, so far so good up to here. You all understand this one up to here?
Yes.
Ini boleh faham lah. All right. So once we have already determined the cutoff frequency, and now we may start to, because we also know that the cutoff frequency is equal to 1 over 2 pi RC. That is the equation. So that means from this cutoff frequency, in order to achieve this, we have a RC, that the value that we need to determine. So because we have two variables, so we need to fix one of it. Let's say we try capacitors, which is 1 nanofarad. This is standard capacitance. Okay, you can try 1 microfarad also, or you may even try 0.44 microfarad or nanofarad. You can try it, but essentially we need to make sure that it is within the range of the design criteria. Okay, previously the design criteria, it has to be in the 1 microfarad to 1 picofarad, this range, and then the resistance has to be from 1 kilo ohm to 1 mega ohm. Okay, so this is just a random choice. Use a 1 nanofarad and then plug it in to here, and then we may now determine what is the resistance. And from the calculations from this cutoff frequency functions, we found that it is actually equals to the resistance is equal to 39.76 kilo ohm. Okay, so 39.76 is clearly not a standard resistance. So we use a standard resistance that is 40 kilo ohm. We round it, and then the capacitors also 1 nanofarad, and we calculate again what is the new cutoff frequency using the standard components. And we found that actually the cutoff frequency is not very significantly affected by this change. It is still close to 403 hertz that we have designed, calculated previously. Right, so now we want to determine what is the effect of these low pass filters on the desired 1 kilohertz. So that's why we substitute 1 kilohertz, and then let's see how is the suppressions, okay, of this desired signal due to the low pass filters. All right, so we substitute into these formulas again. The only difference is just that because we are interested to know 1 kilohertz, so we substitute 1 kilohertz into here for the frequency, and then the cutoff frequency, this is coming not 4003, because we already have a new cut-off frequency. So that is 30,978. And we found that at 1 kilohertz, 97% of the signal is allowed to go through, whereas 3% is cancelled. All right, is reduced. Okay, because V out over Vi is 0.97. So it means that when voltage input is 1 volt, so 0.97 volt is allowed to go. Okay, so it means that over here, that will be 97%. Okay, so you may also double check again. Let's see whether this design can suppress the 100 kilohertz noise. So you may just substitute into the formula square root 1 plus, and then this one is 100 kilohertz, and then divide by 3978. This is the filter that you have designed, and square, and then you press the calculator, and supposedly it is close to 4%. Okay, so far so good. Clear?
Clear, doctor.
Clear? So if you still don't, then I don't really know how to explain it already. So most probably you just go through the lecture video lah. Okay. And if you still cannot understand, then I have to say never mind because this semester we are not going to assess this filter also. Okay, it's just knowledge which is good to have, because in future when you do the experiment, most probably you are going to face these issues where the signal that you are obtaining is very noisy, and then you will know how to get rid of that noise using the filters. Okay. Is that okay, everyone? So I think I'm not going to explain for the others, example 2, 3, and 4. Right, you may just go through it yourself if let's say you are interested. Because this morning I'm just going to show you how can we use this low pass filter in order to remove the noise. Okay. So far, everyone clear? If you don't have any questions, then we take a break, 5-minute break, and then later on I will show you the Tinkercad how to implement these low pass filters according to this design. All right, everyone. All right, so 5-minute break, and for those who have not signed the attendance, please sign the attendance. Okay, everyone, shall we proceed? Are you all ready?
Yes, doctor.
All right. So I'm going to show you the Tinkercad. Right, so you can see the Tinkercad, right? Okay. All right, so I'll just create a new circuit. Okay. And now, before we proceed with the testing, I'm going to first generate the corrupted signal. Okay. Exactly like what is inside this first example. Okay, so I need to have a 1 kilohertz signal, and then another is a 100 kilohertz signal. Okay, so first of all, I'll just get a function generators. Okay, where is function generators? Okay, here this is the function generators, and these function generators, I'm going to create okay, so this is 1000 hertz, that is 1 kilohertz, and then we have an amplitude of let's say 1 volt. Okay, and then DC offset should be 0. So that means this sine wave is having an amplitude of 1 volt, center around 0 hertz. Okay, and then the functions has to be a sine wave. Okay, this is a sine wave, and then to visualize this signal, so I'll just use an oscilloscope. Okay, so this okay, before that, I think I'll just get a breadboard. Okay, so this is a breadboard. Do I need? Okay, I don't need it to be. Yeah, I need it to be huge. Okay, to be long. Okay, so that is the function generators, and then I'm going to plug these function generators into here. Okay, I think before that. All right, I think just straight away here lah. Okay, so red to red and then black to black. All right, and since I'm going, I have a this is 1 kilohertz, and therefore this time preview, I'll just make it to be 1 millisecond, okay, which is 1 kilohertz. Okay, so you can see that this oscilloscope actually shows okay, I zoom in, and you can see that this is 1 kilohertz because one division is 1 millisecond. So you can see that because it is a 1 kilohertz sine wave, actually it is actually like a complete cycle. One complete cycle is one division, that is 1 millisecond. So 1 divided by 1 millisecond, you get a 1 kilohertz. This is a 1 kilohertz signal. All right, as for the amplitude, I am asking it to have a 1 volt. The amplitude is actually 1 volt. And therefore, see that here we have a 2 volt. 2 volt for the okay, 1, 2, 3, 4, 5. 5 grid is 10. Okay, 5 grid is actually all right, time. It only show you the time. All right, so amplitude wise is what okay, so amplitude is 1 volt. So all right, so this means you can see that there is a 2 volt, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 grid we get a 2 volt, and here amplitude is 1 volt. This is half, so it means that 1, 2, 3, 4, half and half, so that is 5. Okay, so there is an amplitude of 1 volt. Okay, so far so good, everyone. How to use this function generator and the oscilloscope? Everyone? Are you all right? Why it is so quiet? Or you are still testing it? Okay. Oh, tengah nak buat ni. Okay, all right. So just try it out to play around with this function generator. So now I already obtained this 1 kilohertz, okay, and it has already been shown in the oscilloscope. Okay, so now I do the same thing. I get another function generators. So this function generator, I would like to this round for this new function generator, I'm going to generate the noise, and according to here, which one? Okay, according to the questions, right? So the noise has to be 100 kilohertz. All right, so this one, the frequency is now 100 kilohertz. So 3 is kilo and then 2. Yeah. So this is 100 kilohertz. And amplitude, the same thing. This round, I think I'll just make it to be somewhere around amplitude of 0.5 volt. Okay, maybe 1 volt lah. Okay, so DC offset is also at the 0. Okay. All right, so now I have another sine wave. And I also get another oscilloscope. Okay, so red to red. And then black to black. So because this round it is 100 kilohertz, and therefore time per division I need to change it. Yeah, I think just a microsecond. 1 division is 1 microseconds, and let's see how is the okay. Apparently it is not enough. Okay, this one I think it needs to be 10 microsecond. Okay, so seems like this one I need to change it. It has to be sine wave. All right. Okay. So it seems like if I am getting a 100 kilohertz my oscilloscope over here, the oscilloscope on top will not be able to capture it, because now the simulator time, you can see that it is actually stepping at the very small time space, a very small step of time. So that's why the oscilloscope on above here, it cannot pop out. Okay, so maybe anyway, I just need 1 oscilloscope only. Okay, so you can see that, yeah, this one I get a 100 kilohertz signal. The simulator time is too small. There is actually a big issue here. All right, never mind. Let's try it out. Okay, so now I have already gotten 2 function generators. So for the negative, I'll just put it over here. Okay. Right, so negative, the ground, it needs to be common ground. And then the negative, the same, just make it common ground to here. And then for the red one, I'll just plot it to here. Okay, as for this red one, I'll just do the same thing and then plot it to here. Okay, so this one, instead of green color, I make it to be orange. And this one, I make it to be a pink. Okay, so these are the two sine wave. I want to combine these two sine wave together. So how to combine these two sine wave? We can use a summing amplifier. All right, so I'll just get the summing amplifier and then rotate it and then plot it over here. And because this summing amplifier, this op-amp requires a positive and negative power supplies, and therefore I'll just get a battery. All right, I'll just get a 9-volt battery. Okay. All right, so I'll rotate this. All right, it's too big, so I'll just okay. And then another battery, 9-volt battery. All right. So now I'm going to get a positive, generate a positive and negative power supply. First positive to ground. This one is common ground. Okay, so this one negative. So common ground. This is the common ground. So common ground. There is the green color. So we just common ground everything together. Okay, and here there is the negative, and therefore I'll just plug it to here. This will give us the negative. All right, so for the negative, I use a black color, and then for the red, there is the positive power supply. So this is red color. Okay, so far so good, everyone. Okay, I just want to generate a positive and negative power supply, and therefore, so if I get multimeters and this negative, I goes to the here for the common ground, which is 0-volt. And then if I measures for the voltage over here, so you can see that actually the voltage that I'm going to get is 8.66 volt. Okay, sorry, I think I have a parcel. Give me a moment. Okay, so everyone, so far so good. Am I going too fast? Boleh follow lah. All right, so this multimeter, you can see that it is actually when it is a 9 volt, we get somewhere around close to 9 volt. Okay, and let's say I measure this black color. Okay, so I should get a negative 9 volt. Yeah, so somewhere around close to negative 9 volt. Okay. The main problem is that because of this 100 kilohertz sine wave, that's why it needs a lot. The step time for this simulation is actually very small, so that's why we need to wait a long time for it to settle down. Okay, all right. So seems like we have already established the positive and negative. Okay, and now this one for the op amp. Okay, so this is pin number 1, 2, 3, 4, 5, 6, 7, 8. So pin number 4 has to go to negative power supply, which is here. And then 1, 2, 3, 4, 5, 6, 7. I think if I'm not mistaken, 7 is the positive power supply. Let me check. LM741, pin number 7, yeah. Pin number 7 is positive power supply. All right, so 1, 2, 3, 4, 5, 6, 7. So pin number 7, I connect to the positive power supply. All right, after that, because I want to sum out these two sine wave together in order to get the corrupted signal. So that means I need to use a summing amplifier. Okay, I can use a summing amplifier to sum these two signals together. So for the summing amplifier, it has a circuit which is looking something like this. So there will be a feedback resistors from the output to the inverting input, and then non-inverting input to the ground. Okay, so we will just do this thing. Okay, so this is pin number 2 is inverting input, and pin number 3 is a non-inverting input. So non-inverting input goes to the ground, so which is the green color. And then inverting inputs needs to so we have a feedback resistors, which is from the output, which is pin number 6. Okay, so yeah, so pin number this one resistors connected output to here, and then this needs to be connected to all right, so goes to the inverting input. Okay, this jumper wire and this jumper wire, let me set it to be blue color. Okay, so we have already established the output, the feedback loop. And now I just need to have a resistors. Okay, at the end, inverting inputs. Here, one resistor to the input, and then another resistor to the input as well. Okay, so I'm using all of them 1 kilo ohm. So that means I'm not going to amplify the input signal. Okay, so I'll just rotate it. And in this case, this one non-inverting input coming to here, and then another resistors, rotate it. Okay, so that is here. Okay, so This one, it needs to go from the input. So this input is the orange color. As for the purple, okay, so I need to go to the resistors over here. Okay, so this is a pink color. Okay, and then this one already go to the ground, power supply, and this is the output. So for this output, all right, and now for the negative, let's go to the ground. Green, and then let's monitor what is the output from the op-amp. Okay, so far so good, everyone. And now let's start with the simulation and let's see what is the signal looks like. So unfortunately, the time step is still very, you can see that the time step is too slow. All right, so that's why we can't really see it clearly. No. Okay, so you can see that because the simulation step time is too slow, so there is a reason why I can't really show you the signal that is corrupted. Okay, but you can already see that this is this 100 kilohertz noise, right? So right now, what you can see in the oscilloscope, this is a noise, 100 kilohertz noise, and then it is fluctuating up and down. Right? Why it is fluctuating up and down? Just simply because it also at the same time have a low frequency signals at the 1 kilohertz. It has already been added it out. Okay, so it seems like can I let's say and make it larger a little bit. Okay, it is very slow. I think we wait for some times. But anyway, that is a corrupted signal that you can see that, right? So you can see that we have a 1 kilohertz low frequency, and then you have a corrupted. That is a very wide band of the that is the high frequency. All right, let's say let's make it to be 1 millisecond. Okay, never mind. It's too slow. Right. Just 10 microseconds. But you can already see that there is a kind of a let's say 100 microsecond. Yeah. Okay, so you can see that for example, this one it is almost 1 millisecond is this is 100 microsecond per division. So for one complete cycle is somewhere around up to here. Here to here. So it's almost half of here. So we have 1, 2, 3, 4, 5. So if let's say 5 multiplies by 100 microseconds, is it complete cycle? 1, 2, 3, 4, 5. Oh, no. So complete cycle is from here until here. Yeah. Okay, almost 1, 2, 3, 4, 5, 6, 7. So you can see that yeah, is a combination of both a low frequency and the high frequency noise. Low frequency is 1 kilohertz, and then high frequency is 100 kilohertz. Okay, everyone? So far, so good? Still with me? Okay, so what I've done so far is just the use of this summing amplifier to sum two signals, two sine waves together. One is 100 kilohertz and then one is 1 kilohertz. So I sum out these two sine waves. Okay. So now I'm going to get a low pass filters. Okay, I'm going to embed the low pass filter that we have already designed in here. Right, so according to the low pass filter, we found that the resistors that we want to use, the resistor is actually 40 kilo ohm, and then capacitors is 1 nanofarad. Okay, 40 kilo ohm and 1 nanofarad. And therefore, we get the resistors, and this resistors is 40 kilo ohm. Okay. So I rotate it, and then I'll just plug it over here. There's the resistors, and then I also have capacitors. So this is the capacitors, and capacitors just now on the calculation we want it to be 1 nanofarad. Okay, so this is nanofarad, so 1 nanofarad. So this is 1 nanofarad resistors. Capacitance, and therefore I rotate it something like this. No. Okay, seems like I cannot extend it, so I think I'll just put it something like this. Okay, so I just connect these resistors and the capacitors together, and according to the circuit for the low pass filters, so you can see that resistors and the capacitors, they are connected in series. Just that this end of the resistors go to the voltage input, and then the another end of the capacitors go to the ground, and the intersection of both R and C, this will be the voltage output. Okay, so the output from the op amp, which is the summation, which is here. Okay, so this one, this is the output, and therefore I just connect it to here. Okay, output going to the input to the resistors, and then for this one, the output from the capacitors, this one needs to go to the ground. So the ground is green color. Okay, and then the output of these low pass filters, which is in the intersection of these two resistors and the capacitors, this goes to the oscilloscope. And let's see how is the graph. So for this one, I'll just use yellow color. Okay, so now let's have a look on the oscilloscope. How is the result looks like? All right, so you can see that if it is without the okay, I'll just do a comparison. So that is the oscilloscope for the after filters, and then I get another oscilloscope. I don't know whether will we be able to do it this way, because it seems like it is too computational intensive. All right, so negative, this one go to the ground. Okay, so green color, and then here oscilloscope is before filters. So before filter, this is blue color, and then here is 100 microsecond. Okay, exactly the same. All right, so you can see that before and after filters, the graph will be, I mean the output signal will be different. Okay, so you can see that before we, yeah, so before the low pass filters, the noise is more significant. And in fact, you can see that the y-axis division, the magnitude is even larger than this one. So there is a 4 volt, but here you only have a 2 volt. And even though it's 2 volt, and you can see that the fluctuations near the low frequency signal is actually smaller as compared to here. So here the fluctuation due to the noise signal is very large. Okay, so far so good, everyone?
Yeah.
Okay, so we have already eliminated this low frequency, eliminate this high frequency, suppress it, and such that only, you can see it still have some fluctuation over here, because the signal is actually, it looks like a little bit thick. Thick is just simply because we are zooming at the time division of 100. So inside is actually very small fluctuations, and this small fluctuation is having an amplitude of 3%, because 3% is a lot. No, this one is 1 kilohertz. Okay, so according to the design, is that only 4% is allowed to go through. So basically, you can see that this amplitude is 4%. All right, so 4% from the previous, from before and after filters. After filters, 4%, only 4% of this amplitude. So high frequency noise has already been suppressed. So far so good, everyone?
Yes.
Yes. Any questions? No. Okay. No. So everyone clear about this topic, the filter? Or you are still trying it out?
Still trying.
Still trying. Okay. So, but anyway, because of the limitations of this platform, it seems like, can you repeat about the fluctuation? Fluctuation about what? Because fluctuation right now, you can see that how to, okay, so I'll just try to explain. Okay, I stop pre. Okay. All right. So I'll just try to explain over here. So before filters, you are getting a graph that looks something like this, right? Okay. Yeah, something like this. And after filters, so you are getting a graph that looks something as this. All right. So you can see that basically before filters, the amplitude over here is bigger. The fluctuation here is bigger as compared to the fluctuation here, which is smaller. Okay, so I can say that this is actually these small fluctuations that is because of the 100 kilohertz noise. So in this before filters, we have 100% 100 kilohertz noise, and then 100% here that is 1 kilohertz signal that we want. Okay, and therefore we summing out these two together, we get this. Okay, but after filters, according to the computations over here, after being filters, we are going to get 4% of 100 kilohertz noise. Okay, because there is when in the filters, it's stated that 4% is allowed to go through. Okay, so 4% is allowed to go through at the 100 kilohertz. And then also from the computation, we also found that when it is 1 kilohertz signal, not 96, I think from the calculation, it is actually 97. All right, so 97% of the 1 kilohertz signal is allowed to go through. So we summing out these two, actually getting this. Okay, so this signal is actually comprised of, or is actually made up by 4% of 100 kilohertz noise, plus with the 47% of, the 4% amplitude of noise, plus with the 97% of 1 kilohertz signal. Okay. Now you clear about the have I answered the question about that fluctuation? Okay. Everyone, so far so good? Any questions? No questions?
No, Doctor.
All right. So if let's say we want to, just now what I've shown you is actually low pass filter, right? If let's say right now I want it to be a high pass filters, instead of okay, just now 100 kilohertz, we tell it as noise, but this round I want 100 kilohertz to be preserved. this is actually the signal that I want. But I have a 1 kilohertz noise. Okay, so what kind of a filter that we need to use? We need to use a high pass filter, right? So to use a high pass filters, actually we can also just do the design. Okay, I'll just stop presenting over here. Most probably I'll just use this, just a very quick go through over here. Okay. Okay, so based on this, the same questions, but I just tweak it. Instead of low pass filters, now I want it to be a high pass filters. All right, so what I need to do is just do the design. What is the difference in the low pass filters and the high pass filter design? So I think I'll just illustrate over here so that you have a better idea how to design it. Okay, so now instead of design low pass filters, so I want high pass filters. So I just changed the question to reduce the noise to 96% at frequency of, instead of 100 kilohertz, now it's 1 kilohertz. So I want to reduce the 1 kilohertz noise to 96%. And then we need to calculate what is the cutoff frequency and then the attenuation of input signal by this filter at frequency of, instead of 1 kilohertz, now it's 100 kilohertz. Okay, so the design procedure is actually the same, right? So VR over VI, 100 kilohertz. The only difference is we change with the formulas. So this one is low pass filter formulas. For the high pass filter formulas, we can see that high pass filters formula is actually this one, F over FC. So on top of here, we need to multiply by another F over FC. Okay, equals to 0.04. And now we substitute 100 kilohertz into here. So we have 100 kilohertz and then divide by FC equals to 0.04. Okay, so let's assume 100K divided by FC is equals to alpha, just a variable. So I get alpha over square root 1 plus alpha square. This is equals to 0.04. Okay, so I square everything. So I get alpha square, and this is equals to 0.04 square, and then multiplies by okay, 1 plus alpha square. Okay, so just press the calculators. Right, so 0.04 square, I get 0.0016. So this one is 0.0016, and then 0.0016 plus 0.0016 square. Okay, and now alpha minus 1 minus 0.0016, so I get 0.9984 alpha square, and this is equivalent to 0.0016. So alpha is actually equals to 0.0016 divided by 0.9984. Okay, and then square root answers. So I get, so alpha should be equal 0.0. Wait. equals to 0.04. Okay, and then because alpha is equal to 100k, and then divide by the cutoff frequency, which is equals to 0.04, and therefore cutoff frequency has to be equals to 100k divided by 0.04, which is equivalent to if I made a mistake, why is the calculations 0.04? So 0.04 square, so 0.0016. Alpha square, so 1 minus 0.1 minus 0.0016, 0.9984 alpha square equals, okay, 0.0016 divided by 0.9984, so 0.0016. 1 divide 0. Wait. Okay, so 0.0016 divided by 0.9984. 0.0016. So square root 0.0016 is equivalent to 0.04. Okay, alpha equals to this, and therefore FC is equals to 100k, and then divide by 0.04. So that means the cutoff frequency is actually 2.5 megahertz. Okay, 1, 2, 3, 4, 5, 6. Yeah. Okay, so cutoff frequency is actually 2.5 megahertz. So it means that we are now having two spikes, and because we want to preserve this frequency at 100 kilohertz, and then we want to get rid of it, and therefore we need to have a cutoff frequency which is very high, so that later on we are able to cut this. All right, because this is just first order filters, that's why the cutoff frequency is not very steep. Okay, so this cutoff frequency has to be equals to 2.5 megahertz. Okay, so far everyone clear? Is everyone clear? All right, so once we have already obtained this cutoff frequency equals to 2.5 megahertz, we may just substitute into these formulas. All right, the cutoff frequency formulas, 1 over 2 pi RC, which is equals to 2.5 mega. And let's assume that, okay, so R actually, you can randomly pick R or C, but C usually has a lesser standard component. So usually, I personally prefer to just try C first. Okay, try to pick the C. So let's assume that I use a C which is equivalent to 1 nanofarad as shown over here. I don't know what is the value. So I just substitute 1 nanofarads into here. So I have a 2 pi R and then 1 nano, and this is equals to 2.5 M. and therefore R will be equivalent to 1 divided 2.5 mega, and then this one divide by the two times pi times 1 nano. Okay, so 1 power of -9. So the resistance that I'm going to get will be 63.6 ohm. So it is not within the range, and therefore I think most probably this cannot be used. Okay, so this is not a very so capacitors equals to 1 nanofarad is not a very good selections, and therefore let's try to be 1 picofarad. Okay, the maximum the minimum value that I can select. So when it is a 1 picofarad, and therefore the resistance will be 1 divided 2.5 mega. All right, and then this one divided by 2 times pi times 1 pico, so 1 to the power of -12. Yep, so I'm going to get the resistors that is I have calculated. So it is equivalent to I cannot write already. Okay, so from the calculation, it is equivalent to 63.66 kilo ohm. Okay, so this one is already within the range, and I'll just use a standard components. Let's say 64 kilo ohm. No, okay, 65 kilo ohm. Right, so I'll just use a 65 kilo ohm. Standard component of 65 kilo ohm. And therefore, the new cutoff frequency will be 2 pi 65K, and then I'm using 1 picofarad, so 1 pico. So cutoff frequency, I'm going to get 1 divided 2 times pi times 65K, and then times 1 pico. Okay, so the cutoff frequency will be somewhere around 2448 1 2 3 4 5 6, yeah, 2.45 megahertz. So it seems like it is quite close to this 2.5 megahertz. Okay, so I think I'll just use this resistor 65 kilo ohm, and then the capacitors is equal to 1 picofarad, 65 kilo ohm. Okay, I didn't check for this at 1 kilohertz how many is allowed to go through, and also how many will be suppressed at 100 kilohertz. This one you may just try it out yourself, but my main purpose is just I want to know what is exactly this value that can actually cut the noise. Okay, is that all right, everyone? So far so good. Any questions about how to design these high pass filters? Everyone clear? Is that all right, or you already blur already? Okay, clear. Okay, so now let's try it out with these resistors and the capacitance. just now I've shown you the low pass filters, and now I'm going to show you the high pass filters. So I'll just take it out. High pass filters, the circuit actually it looks okay. So high pass filters, the circuit is this one. Right, very simple. Capacitors in the input and resistors to the ground. So here there is a capacitor. So capacitors has to be connected to the input over here. Okay. All right. So I think the capacitors, I'll just okay, this one I'll just rotate it. Okay. All right. So capacitor is connected to here. And then for the resistors, then they will be connected to here. Okay. So capacitors, according to the calculation just now, it has to be 1 picofarad. And then the resistors is desired to be 65 kilo ohm. Okay, so I have a 65 kilo ohm and then 1 picofarad. Okay, so the output from the op-amp, which is the corrupted signal, will go through the capacitors, and then this capacitor's output will go to the ground. Okay, so this one, all right, so this will show this oscilloscope ground, and this one is going into the input. Okay, this is the output, and therefore that is the after filters, then it will goes to here, and we can see how is the effect of this is the yellow color. Okay, and now let's have a look how is the this performance of the filter that I have just designed. Okay, so you can see that basically the high frequency is preserved, but the low frequency has already been removed. So that's why you can see that this one is flat. There is no more fluctuations over here. So if I move further in, let's have a look on the high frequencies. Okay, so this one also 10 microseconds. Okay, let me stop and then start again. It seems like it already hang. Okay, so you can see that there is when it is a 10 microseconds, the high before filters, it actually fluctuate with the low frequency noise. But over here, it is the low frequency after you have removed the high frequency sine wave actually is still there. So that's why it is not moving up and down like before filtered. Okay, everyone? So far, so good?